Welcome back to Finite Element Methods, class number 24. So we're talking about Stokes problem, and in this class we really get into some depth on how to approximate solutions to the Stokes problem using our finite element and Galerkin strategies. So the Stokes problem, what is it? What does it look like? We've been talking about this for 3 classes now, and we're looking for a velocity and a pressure that satisfies a differential equation which looks like this. So this is part of a differential equation. These are very important parts of the differential equation called the Navier-Stokes equation. And this equation comes from the balance of momentum, conservation of momentum. The divergence free condition is rather famous. It comes from mass conservation. And then finally, this condition is called the no-slip boundary condition, and this is caused or due to the fact that near a wall or a boundary, the velocity is very nearly in a real system, very nearly zero right at the boundary. Basically, the molecules stick to the boundary so much that they don't actually even move right at the boundary. As you go a little bit away from the boundary, you start to develop things called boundary layers, and the velocity is definitely non-zero. But right at the boundary, it satisfies this condition called the no-slip boundary condition. So last time we talked about the Inf-Sup condition in quite a lot of detail, and we were able to establish using that condition that the solutions exist and are unique, and we also had this fundamental stability. The norm of u plus the norm of p is less than a constant times a norm of f, the operator norm of f, the forcing function. This is a fairly standard type of estimate that one would get. If you think back to the Poisson problem, it's similar to that, except we didn't have this thing called the pressure in the formulation of the Poisson problem. So with this problem in mind, let's move on to the finite element approximation. We started talking about this last time, and I said that we would go over this in detail again in this class, as we will do now. So we're looking to apply what's called a mixed finite element method for the Stokes problem. But why is it called mixed? It's called mixed because we're going to use 2 different spaces and 2 different constructions for those spaces for the velocity space, which is the x space, than we are for the pressure space, which is the q space. So we'll get into that in a little bit. You'll see that at least right away, the first thing that you'll see and find with these mixed approximations is these are constructed differently, and they're also going to have different dimensions. In fact, what we'll show is that the dimension of the velocity space approximation to the finite dimensional velocity spaces is m is always going to be bigger than or equal to the finite dimensional subspace for the pressure. So, in fact, typically it's true that m is strictly greater than n. In fact, it's usually a lot greater than n. You can think it's basically like double the size. Let's establish 2 bases for our finite dimensional subspaces, that for the velocity and that for the pressure. So Bx is phi 1 through phi m. These are vector functions because this space is a space of vector functions. So the velocity function is a vector function, right? If I give you a point in space, it's going to tell you the velocity, which is itself a vector. The basis for the pressure space is what we're going to call BQ, and that is going to be psi 1 through psi n. And again, m should strictly be bigger than n in the general setting. The Galerkin approximation is given as usual. What we're going to do is we're going to use the weak form, as we usually do, and we're going to look for solutions from the finite dimensional subspaces with the test functions being from the same finite dimensional subspace. And again, it's called a mixed method because these two subspaces, XH and QH, are going to be constructed differently. And in fact, this space is, we usually say in the finite element parlance, this space is richer than this space. It has a lot more elements in it. Its dimension is a lot larger than the dimension of this space. So we look for a velocity and a pressure from those finite dimensional subspaces that satisfy our weak formulation. Okay, A minus B equals F minus B equals 0. And the A and B forms are as they usually were, or as they're usually defined for the weak formulation for the Stokes problem. The A bilinear form is a symmetric bilinear form, grad U, grad V in the L2 norm, and B VQ is generically defined as the L2 integral of Q times the divergence of V. So this guy takes functions from the same space, and in fact, it's a symmetric function. B is different. B takes a function from the velocity space and a function from the pressure space, combines them together and gives you a number. Okay, it's clear that that should be a number. Now, what we're going to do is, as we've done countless times, right? We assume that we can expand our solution in a basis. Slight typo here. Don't want to forget the arrow here. That's a vector function. We're going to expand this in the basis Bx. We're going to expand the pressure in the basis BQ, right? As we would usually do. The coefficients for this basis expansion for the velocity are U1 up to UM, and for the pressure, P1 up to Pn. Okay, those are the coordinates of the function in the basis expansion, right? These are also called the coordinates of the function in the basis expansion, the respective bases in this case. Okay. And as usual, what we're going to do is we're going to extract those coordinates and make a coordinate vector from them. In fact, those coordinate vectors can be found here and here. So we're just going to take the coordinates, gather them together, make the coordinate vector u. The coordinates, how many are there in number? There are m for the velocity space, and there are n for the pressure space. So this is the vector of coefficients, also called the coordinate vector for the pressure, the vector of coefficients, also called the coordinate vector for the velocity, with respect to their respective bases. Now, of course, this object here defines how we compute the Galerkin approximation, and it's useful to use that form. It's also useful, especially when we want to write a computer code to find our approximation, to come up with an equivalent matrix vector formulation of a problem. And that's why we're creating these matrices here. So this matrix A is the so-called stiffness matrix, and that's associated, as usually is, to this A bilinear form. The B matrix is a little bit different. It's different because it's the first time we're encountering in this class a matrix that we're creating which is not square. This matrix here is m by n. Again, m is usually going to be a lot bigger than n. Bij, the coefficients of, or the entries of that matrix, are given as follows. Bij is equal to b phi I. Remember, a vector goes into the first slot of the bilinear form B, and in the second slot we're going to put a pressure, and the pressure is going to be psi j. And it's that pressure function, the jth pressure function from the basis for the velocity space. So that's how I'll compute the entries for this matrix A and this matrix B. And as I said, the coordinate vectors are constructed as we usually do. Put those in your pocket. We're also going to create a vector for the forcing function f. Okay, so by the way, so this guy here, what can we say about this vector? Well, this notation is a little bit redundant because notice that f itself was from the very beginning a vector. Okay, so I probably should come up with a separate notation for this, but I hope that you understand the notation. It's a little bit um, maybe confusing, but just don't make the mistake of thinking that this vector and this vector are the same. They're not. So let's at least say, where does this guy live? This guy is a vector which lives in Rm. This object here is actually a vector function. So they are different. All right, so I'm going to describe this vector or this coordinate vector f by its components fi, where fi are equal to the L2 inner product of that forcing function f times the ith basis vector phi I. This is a vector function for I equals 1 to m. That's how I define these coefficients, or these, not coefficients, but entries. Then if you put everything together, it's a short exercise, which I'm sure you can do, so we're not going to belabor this point too much. It's a short exercise to show that once I input these expansions in here and here, I'm also going to create, well, this one I don't have to create expansions for this guy. I can just put in the vectors phi I here. Phi I in this position, phi I here, and phi I here. Here I could use this psi because it's, or psi j if I wanted, it's generic. So if I do that, then I input the expansions, collect terms. What I find is that I can rewrite everything in a matrix vector format. This is the stiffness matrix times the coordinate vector u minus the matrix B times the coordinate vector for the pressure is equal to this vector f, which is encoding the forcing function. And for the second equation, the mass conservation equation, kind of remarkably, I get minus b transpose beta trans or b transpose times u. Of course, I've just added the minus sign actually, I don't have to add the minus sign. I've added it artificially here. Once I have it here, then it comes out below. But whether I put a minus sign or a plus sign here doesn't matter because I have 0 on the other side. So we get this matrix vector problem. And if I want to think about things as I sometimes do in terms of what this looks like in terms of vectors, okay, matrix vectors or blocks of matrices and vectors, we have one big, I can collect everything in one big matrix, and I can think about the pressure and the velocity as being one giant unknown. Because so if I can put these guys together as one giant unknown vector. And of course, this new problem here exists in what space? So so let's see, I want to be a little bit careful here. This is going to be a square matrix problem. So the number of columns is m plus n, and the number of rows is also m plus n. And of course, this vector, the vector of unknowns and the forcing vector is in Rm plus n. So this becomes a square system of equations. We have exactly the the right number of equations for the right number of unknowns. The number of equations and the number of unknowns are equal to each other, as one would hope that they would be. But the problem is we don't know, that's nice, we don't know if this coefficient matrix is actually invertible or not. The coefficient matrix can be written in another way using another kind of notation. This is the so-called block format notation. So let's call the coefficient matrix C. In uh, the upper left corner, we have this matrix A. In the lower right corner, we have this matrix 0. It's a square matrix. So this 0 matrix here is exactly the right size so that the full thing is R m plus n by m plus n. Okay, so then, well, what does that mean in terms of 0? 0 is a matrix of size n by n. This is the 0 matrix of size n by n. Well, this coefficient matrix, what's nice about it is that it is symmetric. Oh, I need to make a little bit adjustment here. Now it's right. So it's symmetric. If I take the transpose of it, I get exactly the same thing back, but it's not SPD. And the reason why it's not SPD is because an SPD matrix has a very nice property that I can check. Every SPD matrix has positive diagonal entries, strictly positive diagonal entries. Well, this matrix does not have strictly positive diagonal entries precisely because of this guy here. Now, the diagonal entries of the matrix A will be strictly positive, but not so for this lower right-hand matrix here, 0. The entries in every position are exactly 0, so certainly the diagonal entries are also 0. How do we know that this coefficient matrix is actually solvable? It turns out famously that this matrix is solvable, and it's got nice properties if I make some certain structural assumptions about my problem, namely if I enforce the Inf-Sup conditions, as I'll show you in a moment. Then we can prove that C is invertible. However, we still can't prove that it's SPD. There's no hope for it being SPD. There's nothing you can do because of that 0 block matrix in the lower right-hand corner. Well, let me make a definition that might not surprise you. Suppose that XH and QH are the finite dimensional subspaces that we want to use for our approximations above. XH is a finite dimensional subspace of X, and QH is a finite dimensional subspace of the pressure space Q, respectively. We say that XH and QH form an Inf-Sup stable pair, Inf-Sup stable pair, if and only if they satisfy the following condition. And this condition is going to be numbered equation or estimate 24.3. And I'm not going to go through and ramble and try to say what this is. It's exactly the same or has exactly the same structure as the Inf-Sup condition that we studied for the full pressure space and the full velocity space X and Q. However, we're asking that these two spaces satisfy this condition for as how can I say it? These two subspaces also will satisfy the Inf-Sup stable condition or the Inf-Sup condition. We know that X and Q, okay, without any restrictions whatsoever, we know beyond a shadow of a doubt that X and Q, here's X, here's Q, satisfy an Inf-Sup now I'm getting tongue-tied, Inf-Sup stability condition. So they satisfy that condition. However, if we cook up arbitrary finite dimensional subspaces of of our velocity space and pressure space, they may or may not satisfy an Inf-Sup condition. So it's a very special pair that we choose, which will satisfy the Inf-Sup condition. What this what this definition is saying is that you can't simply pick these two things arbitrarily. You have to pick them so that they kind of respect each other in terms of their sizes and their approximation power. They can't be chosen independently if you want them to satisfy an Inf-Sup condition. So we say that it's a special pair XHQH that satisfies an Inf-Sup stable pair. And we'll talk in a lecture or two about some choices which do satisfy this Inf-Sup condition for those finite dimensional subspaces. Not all infinite or not all subspaces satisfy it. All right, but suppose that you find a pair that does satisfy this Inf-Sup condition above 24.3. And again, notice that these are the conditions with respect to the subspaces, not the original spaces. Well, if you find that X, H, and QH satisfy that condition, then what we know is that M is always going to be greater than or equal to N. Now, typically, I can tell you the truth is that actually M is going to be a lot bigger than N in practice and in a lot of cases. In fact, a lot of people would say it's safest in that setting whenever M is a lot bigger than N. But at least what we can prove is that if you show that they're stable, the pair, then it must be true that M is greater than or equal to N. So let's see how to prove this. So consider the matrix B. Everything revolves around this matrix B, in fact. Suppose that B is defined as above. Remember, it's a non-square matrix. It's got what? It's got more rows than it has, well, in the typical case, more rows and columns. We're actually going to show that in what we prove. But if we want to prove this, one way of doing it is via the contradiction route. So what we can assume is that M is actually less than N. That is, the velocity space has dimension which is less than the pressure space, M less than N. So that means in that case, B would be a short and fat matrix, right? It would be very wide and very short. So short and wide matrix B. So what do we know about such a matrix that has way too many columns? It has many more columns than it has rows. Well, it must be true from our 571 studies that B, the columns of B are linearly dependent. Okay, they must be linearly dependent. That means there exists a vector, let's call it alpha, alpha not equal to 0, such that B times alpha is equal to 0. In other words, another way of putting it is that there has to be something non-trivial in the kernel. There has to be something that is non-trivial in the kernel of B. That's another way of looking at it. This is just a way of saying that, remember, to make a linear combination of the columns, all you have to do is multiply this matrix times an arbitrary vector. We're assuming, or we know that since it has way too many columns, then those columns must be linearly dependent. So such a vector that is non-trivial must exist. What does this mean in terms of components? Well, for each I, let me write it there. For each I, we must have this. So this is just taking this component by component. So looking at the first row of this. So this is a vector equals a vector. So let's look at the first entry and the first entry, second entry, third entry, right? So what we're doing is taking different choices for I. And so this equation for each I must satisfy this. Now, what is the definition of Bij? Bij is just B, the bilinear form, phi I, psi j. Now we're summing in j, and this doesn't depend at all on j, so we can move this sum entirely in here as we can that coefficient. And if we do that, we can just have an expression like that. Now let's define this thing, this object, because this is somehow special. I guess I could call this Q alpha, but let's call it Q star. Suppose Q star is equal to that thing. Well, that says that B phi I Q star is equal to 0 for every I equals 1 up to M, right? That's exactly what we have right there. For every I equals 1 up to M, B phi I Q star is equal to 0. What does this imply? Well, because these are the basis elements for my basis Q, Bx, we can show just by adding these guys up and using the linearity of B that this implies that B of VQ star is equal to 0 for any V in XH. Okay, because these are basis elements for XH. So use the linearity of B, we can compute this, or we know this fact. Okay, well this implies that if we take the supremum of this quotient, which is the quotient that appears in the Inf-Sup condition, well, because this numerator has to be equal to 0, remember we're putting in Q star, well that must be taking the sup of a bunch of zeros is just equal to 0. But now by the Inf-Sup condition, this is greater than or equal B times the L2 norm of that Q star. What this says, and there's nothing wrong with this inequality that we've generated here. We're saying that 0 is greater than or equal to beta Q star L2 norm. That's fine. Beta can't be equal to 0. It has to be a positive constant. And therefore, the only way that this can be satisfied is for Q star to be equal to 0. But that's a contradiction. The only way that Q star could be equal to 0 is if each one of the phi j's were equal to 0. But we said that's not the case. Okay, so we've generated a contradiction. What does that mean? Well, the only thing that can produce or have produced this contradiction was our assumption that n was strictly greater than m. The number of columns was strictly bigger than the number of rows for that matrix B. That can't be the case. So it must be that m is greater than or equal to n. This is one of the very simple consequences of the Inf-Sup condition for our problem. All right, so the next result that we want to prove, and in fact, the last result that we want to prove, is this one which tells us that the coefficient matrix that we defined earlier, that C matrix, that C matrix was defined as blocks of A, B, B transpose, and 0, is actually invertible. And again, this is kind of going to rely on the Inf-Sup condition, or at least the previous result that we just showed. Suppose that XH and QH form an Inf-Sup stable pair, then there is a unique solution to, oops, didn't mean to do that. There's a unique solution to the Galerkin approximation of the Stokes problem, namely that equation 24.1 that we defined above. All right, so how do we prove this? This proof is long and complicated, but it's useful. It's useful to have seen this at least once in your life, or at least know where to go to look for it. So you might forget everything that you hear here, as I do every year or at least the year after I teach the course on finite element methods, but at least you'll know where to look. Okay, you'll have a good set of notes which explain this proof. So the way this proof is going to roll is that we're going to look at the Stokes problem broken up into two separate subproblems, one for the velocity and one for the pressure. And we're going to do things a little bit differently than we did for the infinite dimensional case. We're going to derive the solution for the pressure problem first, and then we'll derive the solution for the velocity problem second. And everything else is pretty much entirely equivalent to what we did um, for the infinite dimensional case, but I wanted to give you an in-depth and slightly different proof for the finite dimensional version. So let's let Q, again, we're going to try to do the pressure solution first. So let's look at pressures. Let Q be an arbitrary pressure. And let's define a linear functional in the following way. Okay, so the linear functional is actually going to be a functional on the space xh, and it's going to be called L. So L takes velocities and maps them into real numbers. So this is linear functional v LV is defined as it's going to be, remember, Q is fixed, and we're just going to put V in the first slot for that B bilinear form. And once, if Q is already fixed, then of course this just gives us a number. This is the definition of B here. Remember, Q in the second slot goes here, and velocity goes here, the divergence of velocity. This is the L2 norm. So right, if I integrate these two quantities together, I should get a number. So this defines, at least on paper, about a linear operator or an operator. It's clear that it should be linear because this operator is linear and the inner product is linear. So it's linear. It's also, it turns out, bounded. And the way we can show that it's bounded by finding a bound on objects which look like this. Okay, so if we want to calculate a norm for this, we're going to use the operator norm, and the operator norm is going to be the supremum of quotients which look like this. So let's estimate that quotient and show that it's less than some given fixed constant, and therefore the supremum has to be less than that constant as well. So take the Cauchy-Schwarz inequality using the definition of L. So applying Cauchy-Schwarz to this, we're going to get that it is less than the L2 norm of Q and the L2 norm of the divergence of velocity. So we showed in a previous lecture, might have been the last one or the one before that, that this can be written as less than or equal to the L2 norm of the gradient of V. That's actually the norm that we want to use on the space, times a constant, and that constant is simply D. So we proved this previously, so I'm not going to do it again. Well, once we have that, we can just cancel what is in the denominator with that independent of V, right? So now if I take the supremum to find the operator norm, I'm going to see that it's always going to be less than this. So that proves that the linear functional is bounded. Well, now we can use Riesz representation theorem for a certain type of problem. Let's look at this problem. AZH VH equals LVH. L is what we defined above, okay? And we just used, we didn't use Inf-Sup here. This is just the definition of the L. So far, we haven't used Inf-Sup yet, so we'll see where that comes in. All right, so let's examine this problem. AZH VH LVH for all VH and XH. So we're looking for the solution to this problem. How would we be guaranteed that a solution exists? Well, it turns out the reason a solution exists is because this is a symmetric bilinear form, which is also continuous and coercive. This is a bounded linear functional in the same space. So by the Riesz representation theorem, this problem must have a solution. Now, it has a solution as long as we view Q as being fixed. So what this is doing is it's taking every fixed Q that you have, and we're finding a ZH which matches that Q or is somehow connected to that Q. Okay, so Q is fixed, and every time you give me a Q, I'm going to give you a ZH, but it's going to be a ZH which satisfies this problem. Well, this defines a linear mapping for us. Okay, think about it this way. Every time I give you a Q from here, you're going to give me a ZH from this problem. Okay, so that defines a linear mapping, and we're going to write that linear mapping just like that. Okay, T of Q is that ZH which I produced from this problem. So every fixed Q gives a fixed ZH. So this is like mapping Q to ZH. Now, why is this mapping linear? I'm going to let you prove that. I'm going to leave that as an exercise. Okay, the mapping is linear. What we're going to focus on instead is the one-to-oneness of this. So let's see if such a mapping is one-to-one, at least onto its range. Okay. Now it might not, so whenever T maps QH into XH, it doesn't mean it's onto. Remember the difference between the range a of a linear operator and its codomain. So the range is just some part of the codomain. It's not all of it. In any case, we can say that this is going to be one-to-one and onto its range. And so let's focus on the one-to-oneness. To see that T is one-to-one, just take two, well, assume that it is possible to find two different pressures, Q1 and Q2, from that space of discrete pressures, finite dimensional space of pressures, such that TQ1 is equal to TQ2. This implies, because of the linearity that we didn't prove, but I said I'm going to leave as an exercise, that TQ1 minus Q2 is equal to the zero vector. All right, now let's see what the Inf-Sup says about a case like this. The Inf-Sup condition. First of all, let's look at the supremum of quotients which look like this, right? So if T is really equal to 0, right, what do we get? Well, we know that if T is equal to 0, all of these numerators are 0. So this supremum here has to be equal to 0, right? If I have zeros in here, right? If I have zeros in here, then it doesn't matter what I put in any of the other locations. I'm just going to get 0. So I'm going to take the supremum, I just get 0, right? In fact, this is the gradient of 0. Now, remember how we defined that operator T. T was the solution to a certain equation. T was the solution of this equation. So really what we could write here is that T, this guy here is just going to be T of Q. That's T of Q right there. Okay, so what is this guy? That is A of T, Q minus Q, Q1 minus Q2, and against V. Okay, according to my definition of the T operator, that's just going to be L. But what was L? L was defined simply as Q divergence of V. Okay, but if it's not Q in this case, because it's the difference of two Q's, Q1 minus Q2, divergence of V. But now, what do we have? Let's see, what's 20? Yeah, 24.4, that's my definition of T. That's where we applied it there. Now we go on to 24.3. That is precisely the Inf-Sup condition, right? Let's make sure we get the number correct. It's the Inf-Sup condition for the pair XHQH. So Inf-Sup condition says that, but now, based on this construction, we see that 0 is bigger than b times L2 norm Q1 minus Q2. A similar argument that we to the one that we used previously, or in the proof of the last lemma. Well, that says that this element can only be equal to the 0 vector, or the 0 function in L2, or in QH, I should say. So this function being equal to 0 means that Q1 is equal to Q2 in QH. But what does that say? That says if I have this, then the only way that it can happen is if Q1 is equal to Q2. That's what we mean by one-to-oneness. Okay, so T is 1 to 1. Now let's define a space. Define the space Z to be equal to the range of T where its domain is QH. So this is just like saying ZH is the range of T. ZH is the range of T. So if you want to make a note, ZH is the range of T. That's it. What do we know about these spaces? Well, T is 1 to 1 and onto. So that means if you know that means it's isometrically isomorphic, right? So it's an isometry between QH and ZH. That means that, well, if you know the dimension of QH, you automatically know the dimension of ZH. We know the dimension of QH is exactly n, so the dimension of ZH has to be also equal to n. But ZH, what was that? Where was that? The range of T is a subset. Okay, you can write it right here. The range of T is a subset of XH. The range of T lives in XH. And now we're defining below that ZH is the range of T. So ZH must be a subspace of XH, and it has dimension M. Well, now we know from the previous result that this is a smaller space, right? It's a subspace. Now, we don't know if it's exactly a proper subspace because all that we proved previously is that M is bigger than or equal to N. They could be equal to each other. But generally, as I told you, M is a lot bigger than N, usually double the size. So this is really, in practice, going to be a true vector, proper vector subspace of XH. That means, well, for one thing, it has a non-trivial orthogonal complement. What do you guys remember what the orthogonal complement was? So in finite dimensions, it's not that hard. In finite dimensions, we can use an inner product to find an orthogonal complement. Usually you use the Euclidean inner product, but here we can use any inner product that we want. So we're going to define the orthogonal complement of ZH, and that's going to be called ZH perp. It's going to be the set of all vectors in XH that are orthogonal through this inner product to the vectors of ZH. ZH is the orthogonal complement, or ZH perp is the orthogonal complement of ZH. So that means that we can write XH is equal to ZH direct sum ZH perp. Let's see, what was the dimension of these guys? So this one had dimension M. This we just showed is dimension N, and this is dimension, has to be M minus N. Okay. Now, theoretically, so far, this could have dimension 0. It could just be equal to 0. That would say that the only thing which is orthogonal to everything over here is the trivial subspace, which is just the subspace comprised only of zero, the zero vector. Okay, so we've just constructed that orthogonal complement. Great. We know that we can decompose the space like that. Great. Now, I guess I lied. We were dealing with the pressure first, but we are going to construct the velocity solution first. So how do we construct the velocity solution? So this is not necessarily, well, I should say, this is probably not going to be evident or self-evident. It's not obvious why this is why we're taking it to be this way. But this is what we want. So, and you'll see that comes out in the end. We're going to define UH, first of all, to be the unique solution in ZH perp to this problem. Okay, AUH VH is equal to FVH for all VH in ZH perp. Does this have a solution? The answer is yes, it has a solution because this is very clearly going to be a bounded linear functional on this subspace. This is a coercive continuous bilinear form on the parent subspace XH, and so it'll be a coercive continuous bilinear form on any subspace as well. So this forms an inner product on that subspace. And we said an inner product can always be made, there's always a representer so that a linear functional is equal to an inner product times that with that representer in the first slot. So this is guaranteed by Riesz representation theorem. And by the way, when we examine the infinite dimensional space, Navier-Stokes problem, we constructed the velocity solution in exactly the same way. So the work is exactly the same. Now we're going to construct the pressure next. So we're going to define pH, the pressure for the Stokes problem, to be the solution of this problem. At first, when you look at it, it's not clear that a unique solution exists to this weird problem. So this here is BWHPH. That's what this guy is. And we're setting that equal to this inner product of L2 functions. The test function space, WH, is going to be ZH. And so how do we know a unique solution to this guy exists? Okay. Well, you don't know right away, but we can use this right-hand side to construct a ZH, which we know this is going to exist. By Riesz representation again, this is a bilinear form on any of the subspaces of XH. And here are two subspaces of XH, right? It's a not just bilinear form, it's a continuous coercive bilinear form, and also symmetric. I forgot to point that out. And so by the Riesz representation theorem, as long as this object over here is a bounded linear functional, which it turns out to be, I hate to use all these functional analysis and PDE terms, but on the other hand, we're not using them gratuitously. We're using them because they make our life easier when we want to prove something. In any case, Riesz representation theorem says that a solution to this problem exists. Remember, we're trying to get at the fact that this P exists. Well, now we've got this Z. This guy is unique. This guy exists and is unique, this ZH. And what space is he in? He's in this space, ZH. Well, we know that there's a mapping P which takes this pressure space into ZH, and it does so in a unique way. It's a one-to-one onto mapping. So now we're going to let pH be the unique solution of this equation. Okay, this guy right here. How do we know a unique solution for this exists? Well, we know that T is one-to-one onto from QH to ZH. Therefore, there has to be a unique element over there mapped to this unique element here. And by the way, but using the definition of T, the definition of T says that that pH satisfies this equation. But we know from here, 24.7, that this equals that. So that says that our original equation, 24.6, which is basically the combination of these two, has a unique solution because P has to be connected to this unique ZH. So that says that 24.6 is unique. So here's what I did. I constructed first the velocity function, and now I'm constructing the pressure function. Both of them exist and are unique. And basically, in both cases, we use the Reese representation theorem. We did, of course, use Inf-Sup condition whenever we were showing that this T was one-to-one onto from QH into ZH. So Inf-Sup is in there. It's just buried kind of deeply in the structure of it. Well, now we have a UH and a pH. All we have to do is show that those are the solutions. So now we're going to put those together to produce the Galerkin approximation. What we're first going to do is in our Galerkin approximation, our test functions were from XH. So I'm going to take an arbitrary test function and I'm going to break it into its orthogonal decomposition that's guaranteed for us because we're in this finite dimensional space XH. Remember, XH is equal to, XH was what we said it was ZH, direct sum, ZH perp. So this first object is going to be from ZH, and the second object is going to be from ZH perp. So I hope everyone's okay with that. Arbitrary, and we can break it up. Whenever I take this arbitrarily, this has a unique projection into this space, and it has a unique projection into this space as well. Okay, so it's a little bit like saying these two functions are also arbitrary. Okay, so VH is arbitrary. Then let's look at this this bilinear form. A, UH, VH. And UH here is going to be the solution that we got from 24.5. Okay, from 24.5. So the first thing I'm going to do is I'm going to break VH into the sum, this direct sum that I decided was possible above. Now, UH, we said, is in ZH bar. If I look back at the solution of 24.5, we said that UH had to be from ZH bar, or not ZH bar, ZH perp. Well, if UH is in ZH perp, then that means it's perpendicular to anything in ZH. Well, that part of the test function that's in ZH is certainly going to be perpendicular or orthogonal to UH in the A inner product. So that's why that's why this term goes away. That's because of the orthogonality. Now we're going to use the definition of our solution from 24.5. This is arbitrary here, so that doesn't matter that it's arbitrary. It's true for any of these guys. So this is equal to that according to 24.5. This is the forcing function, and all we need to know is that this guy is in ZH perp. All right, now the next thing I'm going to do is I'm going to rewrite WH2 as VH minus WH1. And that can be gotten from right here. So WH2, if I take this guy, move it to the other side, then I get VH minus WH1. So replacing WH2 by VH WH1 and using the linearity of the inner product, I get that this is the difference of these two terms. Okay, just by the definition of VH. Next, what do I want to do? Well, by the definition of the pressure was defined as being equal to that object, okay? Minus the pressure. Actually, let's see, how did I define it? Equals with a minus sign there. So did I make a mistake? Yeah, I think so. Right. So this one, that should have been plus that pressure, right? And then plus and plus. I think that's right. Pressure is equal to, this term is equal to minus that, okay, by 24.6. Again, let's double check. Minus sign, yeah. So the minus sign changes to a plus. What am I doing here? Well, what you can show is that the pressure, because it's from the pressure space QH, is orthogonal, well, kind of orthogonal. If I formulate or form this bilinear form, this is always going to be zero. Okay, this whole term is going to be zero. And the reason why is because P is from the pressure space QH, and this is from ZH perp, ZH perp. So this is quote unquote orthogonal to this guy. I'm going to prove this below. But it's really just follows from the definition of T. So that's why I can add this term. Now, just use linearity to recombine these two terms, add them back together, and what do you get? You get VH. But that's just exactly what we would expect for the solution um, for the Galerkin approximation of the Stokes equation. If you go back and look at it, then what is this term here? This is just B, and of course you move it back to the other side and go back and look at the formulation of the Stokes problem. This shows that this U and this P satisfy the first equation of the Galerkin approximation of the Stokes problem. Okay, well, that takes care of one equation, but you have two, right? You have two. So furthermore, we can show that that second equation also holds. And the reason it holds is because, again, this is in ZH perp and this is in QH. And I said every object like this is automatically zero. And this is automatically true for any QH in QH. And so if that's true, then the velocity pressure pair that I created here satisfy the Galerkin approximation of the Stokes equation. How do we know this? How do we know this? Well, let's see. So I guess I didn't prove it, but I want to state it at least generically. Something I already said. The proof is like two lines, but it does require going back and having a small little re-examination of it. So what I claimed is that you can prove the following. For any QH in QH and any ZH in ZH perp, sorry, any VH in ZH perp, then this object is always going to be zero. So that's why this object is zero, and it's also why I could add this guy back without any impunity. And if you buy that, then we're done. And the theorem is proved. We have a solution pair. Don't get too nauseated. Sorry. That satisfies this equation. That solution pair satisfies this equation. The reason why uh, this should be a plus on the other side is when I take this term over to the other side, I get a plus sign. Okay, so I definitely had a typo, and I think we've definitely fixed it now. So that's it. That's where the Inf-Sup is used to prove that our Galerkin approximation um, exists and is unique. And so next time, what we'll be interested in is showing that our approximation is stable. So that's one thing you should always want to prove. And then, so now we have the solution, our approximate solution exists and is unique. Next, we want to show that it's stable. And then finally, we want to show that it's a good approximation of our true solution. So that means we want to prove something like a Say's lemma. But it turns out proving a Say's lemma is pretty tricky. And that's kind of what is involved in homework, the homework problems. But as I said, when we meet next time, I'll review a lot of that and I'll give you a lot of insight about how to prove that those two homework problems. So we'll end it there, and you can turn on your your cameras, and I'll take your questions.